Okay. Hi, my name is Ian, and today I'm going to tell you about the HR, this one, diagram. And so this HR diagram just looks like this, and we can know the temperature from this. The left is higher temperature, and the right side means lower temperature. And this is luminosity. This part is luminosity, and this is the higher, and this is the lower. And so, what is HR diagrams? And this table is the start of the starter evolution, and it's by this person and this person. So combine these two names, we can know the HR diagram, and plus the temperature of stars against their luminosities. And each stage change in the temperature and the luminosity of the star. It means that this means different stages. This is the main squares, and this is the supergiant and giant and white jet. This
white
dot, and these four stages, it represent the different luminosities and temperatures. And so the astronomers can know stars' internal structures and evolutionary stage by determine its position in the diagram. So we can only observe the luminosity and color of the stars, right? So by detecting the plans of the colors, we can know its temperature, and by observing the luminosity of the planet, we can know the distance of the stars. Also know the absolute luminosity. So we can combine all the information. We can know the location of the planet. And furthermore, we can detect the radius and know its size. And so, as I say, this is HR diagrams. This is also the spectral class. It means the position. So, if you want to explain this, you can also say B and 10 minus 2.
10 to the minus 2.
10 to the minus 2. And this is temp. So, as I say, left is a high temperature, and the right is a lower temperature. Okay, we know the surface of the temperature. So, this is the luminosity. This is higher and this is lower. Then the main squares.
Then what?
Main sequence. This is the main sequence. Is the most bigger one. And 90% of the stars is in this main sequence. So the main sequence changes from the upper left to the bottom right. Upper left to the bottom right. So this one. Demand.
Dominate
the HR diagram. And about 90% of their is burning hydrogen into helium. in their course. And main sequence start have the this MK luminosity class label V, just like the past. This means the location, and it just okay. We know the main sequence, so as I say, we can just use all about the information to detect its radius. So we also got its size. And last, we have to know what's the life history of the sun-like stars. So the first is the stellar nebula, and so we have to detect his mass. If the low mass, it will become the red giant and the planetary nebula, and the last white dwarf. And if it is a giant mass, he have the giant mass, and he will become the red supergiant, then supernova, and in this, he may become the Newton star. And if this planet become Newton star, it will go back to the first and become the stellar nebula to go loop. And if you become the black hole, it's a black hole. Yeah. So this is the end of my presentation. Thanks.
Okay. Hang on, you have to stand here. Group A students, any questions from you? Comments, questions? If not, I will go through each of you. Okay, Hank.
So, what kind of things we need to know to understand the...
Again.
So, what kind of things we need to know to understand a star's its age or its just its age?
What kind of information do we need to know its age?
We can use the distance and absolute luminosity. Use these two information, we can know the location of the planet. And if we know the location of the planet, we can detect its radius. If we know its radius, we can know its mass and age.
You are talking about like a 2 years old, 3 years old, or a life stage. Life stage or absolute age. Which one? Life stage. Life stage. Okay, then your answer is right. Okay. Who else? Okay, Ray.
Can you turn to the HR diagram?
Which page?
HR diagram. Yes, this one.
This.
Yes. And you say the sequence is burning the hydrogen and
To the helium.
helium. So in the supergiant star, they burning the other material or what?
It's a good question. What are the stars doing at the giant or supergiant stage?
Is this in the raw materials? Okay, I didn't read about it. I didn't read enough, so I don't know.
Okay, do you know anything about this? Or is it a comment or a question from you?
I guess I guess it burn another element to become a supergiant. Is that true?
It's not absolutely true. It's depending on what kind of giant. We will talk about it in detail during my lecture. Further question from Group A students. Any? I hope to collect 3 questions. Let's see. Kim Zhen.
White dwarf. Yeah. Can you explain why its position?
Can you explain why white dwarf is in this position?
When raised in the rest life of the plant, and his surface temperature will go down. Just set temperature become colder, and his luminosity become dim. Lower, become lower. So it will in this way become this just to the top right and just move to the bottom left. So as I say, his temperature totally different.
Total different.
No. Yes, temperature and become this, and this image become this. Yeah.
Well, we will explain later what kind of temperature this temperature refers to. Okay, it's actually written here. It's very small text. Surface temperature. So it means the surface temperature of the star. And you can imagine, for example, for Earth, the internal temperature of the Earth is very different from the surface temperature. The same applies to a star. So you might wonder why the supergiants have lower temperature than the white dwarf, which is at the final stage of the star. And it's actually related to the size of the star. So we will talk about it later. Okay, Group B students. Zhiying.
I want to ask, how do you know it is a massive star or not, or an average star? Because in same luminosity, then there is a supergiant and the average star. Then how do you know the size of the star?
Right, I have how do you know the size? Actually, that was my question too. How do you know the size of the star? Is there any physical equation, something like that? Okay, so hint.
So many questions.
Okay, the easiest question is, how do you know the size?
By observing
By telescope?
his absolute luminosity.
But a star can be very shiny and very small, or?
Yeah. And distance. Okay, I have no idea.
All right. Anybody comments for that question? Anybody read about it? No? Group? Okay, Kevin, is comments or question?
that question.
Okay.
Can I draw on the blackboard?
Sure.
If a star is a gas, so it's not like our planet is the rock. So maybe it's a core, so this is all gas, but it is burning. So what we see is this one, the light. We see a light of the star. So this is the basic of this size. So how can we know about this size, about this luminosity, and what else? It's on my PPT. I forgot. And luminosity and the surface temperature. And how do we know the surface temperature?
Hang out for a minute.
Okay.
The spectrum.
The surface temperature. How do we know the surface temperature is about what you just said, the radiation, and just put on our Earth. And so combine this, I forgot one reason. But combine the three reasons. Combine the three. I forgot one. So you can know the size of the star.
All right. I hope the video record. I'm not sure if I fully understand you, but this is to the point. What you observe from a star is not the core, but the outer atmosphere. And this is related to this here. And actually, you say 3 parameters. This is the first parameter, the temperature. The second is luminosity. And actually from that, you can, and actually luminosity is determined from brightness. 就是表观的亮度. Last week we talked about it. When you see a light, for example, the light from the projector, what you see is as an observer. And the intensity you sense, it depends on the distance. So you, of course, to know this, you need to know the distance. So once you know the brightness, the distance, and the surface temperature, you can actually calculate the size, as this diagram, this graph shows. And I will tell you later what kind of equation this is about. It's a very simple equation. All right. So Kevin, thank you for your comments, I would say. Any further questions, comments? No? Okay, let's take Ian.
Good morning, and I'm Ethan. I'm in Group B. And first I explain what is isotope and what is isobar. And when we say
Use the pointer,
when we say isobar, we will there's 2 points. That one is the number of the protons, and another is the number of the neutrons. And when we say the isobar, we will is that being they have the same number that protons plus the neutrons, like the Z plus and we will call it A, so they have the same A. Okay, and the isotope is that they have the same protons, like the same Z. And in this diagram, that the isotope is that they have the same Z. So here, they are the isotope in one element, and the isobar is that these two, they have the same number of the proton and plus the neutrons. And I have to explain the this about to use this diagram. And what is the stable isotopes? Like we will know in this diagram, the black one is the stable one. Like we usually see the stable elements, and in this the gray one is we will call the radioactive isotope because they are not stable. Maybe there will be alpha decay or beta decay or also spontaneous fission or elegant capture. Yes, because okay, I will say why they are not stable or unstable. Okay, and the band of stability is this, and the relation between N and D, we can see the X, and is this?
X-axis.
X-axis is this one, and the Y-axis is this one. And we will see this N equal to Z, and when this band, this the stable black line, you can see in the first they are much equal. That means in the hydro, helium, and maybe lithium, they are equal to this. But the forward will they go more neutral and no much more protein. Yeah. And I'm going to explain what is the iron stability, and it's the picture like it. And you can see it's a little bit. I think it's the same diagram. Yeah. Okay. So what is the iron stability? It's first is a prediction to find some heavy elements, super heavy elements, and maybe that because we know the much bigger elements, the half lifetime will be very short. So, but in this diagram, they want to find a very longer half-lives than the super heavy elements. Yes. And we can see this part we will call the peninsula. In Chinese it's called 半岛. And what is this diagram to predict is to predict the island of stability, because this island is not defined yet. This is only the prediction of the scientists. Yes. And now it predict it will be this big in here. Yeah. And okay, let me talk about why here don't have such haven't found it, because in the nuclide there's we will know there's two particles. One is neutron. I have been neutron and protons. And there's two forces. One is the cohesive force, and we will call it Coulomb in this lecture. And this force will put two particles together. And another is called the electromagnetism, and where there is two same charge, same charge, and they will not to get very close. They will be repulsed. Yes. So in the first, because there's little about the little about protons. So there will be much more stable. In the when the protons come bigger than the this one. This one's the force will much bigger than this one. So the nuclide will be fusion. Yes. And this a short explain about the alpha decay, beta decay, and the electron capture. Yes. And beta decay is called the protons. The neutrons become the protons and one electron. And the electron capture is called the proton and to the neutron. And alpha decay is called -2 neutron and -2 protons. And the first, because we find this phenomena, so we will call it eject helium atom. Yes. So we also can call it helium decay. Yes. And this can be used in here. Because this side there have a lot of much more protons, so they have to decay the protons to the neutron, and this side they have much more protons left, so they have to decay to the neutrons. And this side, because the nuclei is so too big, so they have to decay protons and neutrons. And if it's too big, there will be a spontaneous fission. Yeah. So spontaneous fission is to break into two particles. Yeah, one particle to break into two particles. Okay. And I think to the last, this diagram is going to tell us we will know every element and what is the origin, what is caused by the cosmology, cosmos. Yes. Where will they come from? Yeah. And I think this is one part the professor will teach today. Maybe. Yeah. And thanks.
Okay, thank you. Okay. Group B students, any comments? Okay, Vincent.
I have a question. I have two questions. The first one is about the isobar. Can you show the slide? So, in an isobar, each isotope has same mass number, right? So we know that, and why do we have to know the isobar? I mean, is any reaction or something about isobar, or it's just a line that each isotope have a same mass number? This is my first question.
Okay, in short, what's the importance of isobar?
I don't know.
What do Okay, I can tell you one. It's like the test of government official examination. 公务员考试会考. Okay. But anyway, anyone knows something about isobar? It's actually very important.
Because the decay, no matter the electron capture or the beta decay, the nuclei mass will not decrease. I mean, during the process, they increase the proton number and decrease the neutron number. And the isobar means on this side they have the same nuclei mass, and because of the decay will not decrease the nuclear mass. So that means if the elements are radioactive, they will decay through the isobar to the band of stability.
Right. Can you show the chart where you have this alpha decay, beta decay, and no, the graph. Right. So, oh, it's not clear here. You see the electron capture and beta decay. It's actually along the isobar line. That's the reason why you need to know isobar. That's a theoretical reason, but there's another reason. So I can tell you here. Most of you probably would not have experience with mass spectrometer, 质谱仪. However, you need to know, nowadays, like you want to measure, for example, many elements or even organic compounds, you need to use mass spectrometer, which measure a substance based on its mass. However, the concepts of isobars tell us that even when an isotope measures a specific mass, this mass can refer to different elements. That's the importance. Okay? 所以那个同重数 in Chinese 对于质谱仪的测量是一个重要的概念，就是你不能认为某一个质量就只有对到一个元素，它可能对到很多个元素，就是端看这张图告诉你它可以对到什么元素。Okay? Second question.
Then my second question is about the last slide. Yeah, it's one. So my question is what is what's that? Because the alpha decay is the heavy element, and the spontaneous fission is also the heavy element. So how do we know if there is a heavy element? It go alpha decay or go spontaneous fission?
Is the question clear?
Maybe I don't know well, but I think if there's an enormous nuclear, maybe you will break in spontaneous fission first, and if there's an element that we know, and will be alpha decay first, like the uranium. Yeah, uranium. Yeah, maybe. Yeah, I think.
Okay. Actually, I want to clarify. You have this spontaneous fission, 自发性的核分裂. Although it's plotted here, actually it can also occur here. As long as it's a heavy element, it's possible. So actually, I would say it's whether a nucleus undergo spontaneous fission or alpha decay, it's the nature of the nuclei itself. Alright? But here, because there's no stable element, right? So you can almost be certain that the nucleus here are not stable. So it's very likely that all the nucleus here, they have the ability to undergo spontaneous fission. But spontaneous fission is certainly also exists here. Right. 2 questions already. 3 questions? Any? Okay, 志英. Lady first.
I want to ask, can isotope happen electron capture and beta decay? A same isotope, can it happen electron capture, both electron capture and beta decay?
Is your question like this? Can an element be produced by both process? Is that your question? Or not?
Isotope happen both this
Or what kind of
reaction.
what kind of element will undergo beta decay and what kind of element? No?
Can happen both.
Both. Okay.
Both.
Is there any element that can undergo both electron capture and and beta decay? Okay, Ethan.
I think it will go on the isobar. Yes, because isobar can also beta decay and electron. Yes.
And is there specific elements that can go this way and that way?
Only one specific. I
Or
don't know.
both, or one specific, you don't know. Okay. To be honest, I don't know either.
I have checked before. Then I find it that Mn is Mn what?
Can you
It's Mn
manganese?
manganese 54
54
can happen both reaction.
But the
CO CO is
cobalt
cobalt or cobalt 58 cannot happen. Just can happen the electron capture only. So I was so confused.
Okay, but manganese 54, as you see here, we have manganese 55. Right? So 54 is probably here, right? And it's radioactive. Right.
Yes, the manganese 54 can happen the beta decay become iron 55. That's
Uh-huh.
54 and happen electron capture become the CR.
Chromium 54.
Yes, both reaction.
That's something new to me. I always think it's only possible for one direction. Okay, thank you for your comments. Okay, and Ray.
First one is in this picture, and we can see the even numbers of protons have more isotope, and the odd numbers of protons has less isotope. And can you explain why have this phenomenon?
The question is clear, right?
I think it has been in the lecture, but I have read it. I don't read it. Yeah. It is some principle. Yeah. Yes.
You have an answer to that?
I don't have, and I see it, but I don't read it.
Okay.
And the second question is you talk about the nuclear force. That slide. Can you turn to that slide? And what is the difference between the gluon force and the strong force? They both is the nuclear force.
So is the cohesive force from gluon is equivalent to strong force?
Maybe I guess. Is there? Because this kind of the term, I think is the old one. Yeah, and maybe there will be some new term. Yeah.
You want to respond to that? Answer to that?
I don't know either.
Yeah, I would say the process involving gluon is the strong force that you're talking about. Okay, A students, I think we have a lot of questions already. A students, maybe? Okay, thank you, Ethan. Okay, today we want to talk about nucleosynthesis and stellar evolution. And Group A students already handle stellar evolution, this topic, and Group B student part of the nucleosynthesis. And now I try to give you a more systematic understanding of this topic, but you already know the details. Last week we talked about the Big Bang, and this is some imagination from the scientists, but of course it is some scientific base, like mostly computer modeling. I don't know if any of you have read a book written by Hawking, the 最初3分钟. It's a very famous general science, public science book. And I think in that book he also described about what scientists imagined about what happened right after the Big Bang. So it says like temperature was so high that no atoms existed, only fundamental particles, like a quark, okay, that kind of thing that you never need to use, okay? And even smaller than neutrons or protons. There were no atoms or elements yet. And then the next question is, how did the universe then pass from this state where there were only fundamental particles? This is completely unfamiliar to us, to the collection of elements we find in the universe today. So this will be the topic for this week and next week. And the answer to this question is the stellar synthesis theory. And it's actually based on the textbook. It's a very solid scientific theory. If a full score is 10 points, then this hypothesis has 9.9. Oh, very high score. But before that, you need to review or remind yourself a little bit about descriptive atomic physics. Okay. Here, Ethan also showed this table. It's a periodic table. And here, I use the title, Planetary Reality. There's a pun here. Pun, P-U-N, 双关语. Okay. So, for example, if you go to a conference, 国际会议, usually there will be many different sessions going on at the same time. Like this room, there will be a topic. Next room, another topic. But very often, there will be a very big meeting room where everybody just go to that talk. Usually, that talk will be considered very important, and that session will be called planetary session, which means 你可以把它视作是，就是说最重要的，然后大家都要参与的。Okay. And here, planet, we also know the other meaning it means 行星. Okay. So here, planetary reality means it's important and it's also on the planet, which is atoms are neither created nor destroyed on planets. However, atoms can be created in stars, not in planets. So that's what you already learned from the discussion before. And Ethan also talked about these fundamental forces. So we know we have strong field and this and that, electromagnetic fields. And here I try to give you some visualization of what's going on. We have lithium-7 here, proton, neutron, and if you zoom in, if you are able to zoom in and nucleus, then you will see gluon. And these are strong force, and the even more fundamental particles will be quark. So, if you still remember what you learned from general physics, then it will tell you, okay, proton and neutron are convertible, and basically they are consisted of quark. And what binds the nucleus together against these positive charges from protons are so-called strong force. And there is another force called weak force. It's actually a kind of convertibility, 可转换性. That is, proton and neutron, they are not like I am I, you are you. It's rather they can convert to each other. So as you learn from beta decay, and the inverse reaction is electron capture. So at a more fundamental level, that actually involves the removal of some more fundamental particles that you don't need to know, like something like a boson or anti-neutrino. Okay, I don't want to talk about it. You only need to know that they are interconvertible. Alright, so we talk about strong force. It binds the nucleus together. And the weak force, which means it regulates the convertibility of neutron and protons. We have two more fundamental forces. One has an infinite distance over which it operates, and the other two. Where it is important? Everywhere, or well beyond the atomic scale, large masses needed. So, what is this and what is that? And look at the relative strength. Strong force, if it has 1, then this force has 1 to the 137. Weak force 10 to the minus 5, and this one 10 to the minus 39. Okay, what are they? It should be easy. Jackie, what's this and what's that? If you don't know the English, you can also speak in Chinese. 4 fundamental forces. Okay. You don't know? Okay, I saw Ray raise his hand. Okay, what's that?
The last one is gravity.
The last one. Gravity, right?
The second one is the 库仑静电力.
Right. Or we say electromagnetic force. Okay. That Ethan also talked about. So these are the 4 fundamental forces that people need to think about when dealing with nucleosynthesis. So here, electromagnetic force. Here, gravity. Okay? Energy consideration. Here, on Earth, we mostly observe only chemical reactions, which take place only at the electron level. When we see A substance is converted to B substance, they only change their electron configuration. And the reaction temperature range is 10 to 10 to the 3rd. So 10 to 1000 degrees. Now you can imagine, for those who have been in a lab, 有参加实验室的, you can imagine what is the highest temperature you ever use in your lab? The answer is, for example, in my own lab, the highest temperature I ever used in my lab is 1200 degrees. That's the maximum. So it's actually quite low compared to the temperature you need for nuclear reaction, which is higher than 10 million. 10 million, right? So it's really, really high. Therefore, the only way to raise temperature is to increase the velocity of a particle. Once it moves faster, its temperature will also raise. So artificial nuclear reaction can only be induced by explosion, 爆炸, or particle accelerators, 加速器. That's the reason why they want to study fundamental physics. They really need to build really large particle accelerator in order to reach this temperature. We stop here and we come back based on my watch. 12 after 11.